Hey everybody, welcome to another equilibrium calculation. In this video I'm going to show you how to calculate the value of K. I'm sorry, not the value of K. In this particular question what we're going to do is we're going to find, not K, but all of the equilibrium pressures at equilibrium. So we're going to find the pressures at equilibrium for everything, so for all three substances. So in this case we know what K is. We've got the Kp and we know that it's a very small number. We're going to use that to our advantage. So we're going to keep in mind that that's a very small value. So Kp equals 6.8 times 10 to the minus 9. Okay? So what we're doing is we're starting with this phosgene gas, okay? And we're going to allow it to decompose into carbon monoxide gas and chlorine gas. Now we're going to do an ice table here, okay, and we're going to take our 1 ATM, that's what they're starting with. So keep in mind we're going to do the same thing that we do anytime we have K. Just because it has the P down here doesn't change any rules really, it just means that we're dealing with pressures, so instead of concentrations we're going to use ATM here. Now we're going to just follow the same rules we did before, so it's going to be carbon monoxide, but instead of writing it as concentrations, what we're going to do is we're going to write it as partial pressure of carbon monoxide times the partial pressure of the chlorine over our partial pressure of the phosgene gas. Now everything's a 1-to-1 ratio, so I don't have to worry about any coefficients and putting things to the particular powers, but if there was a 2 here, I'd put a 2 here, down here, just like I would for any other equilibrium system. Alright, now I don't have any carbon monoxide and chlorine, so they don't tell me that there's any of that added. I just have this phosgene gas that's added. And since that's the case, I'm going to shift to the right. This is going to go down, this will go down, and this will go down. I'm sorry, take that back. These two are going to go up. So this is going to decrease, and these two will increase as the reaction progresses to the right to produce the products. Now, to figure out the equilibrium values, I need to know a little more information. Well, it would be nice if I knew one of those, if I was able to measure them. But for whatever reason, I can't, and I don't have that information. So how do I handle that? Well, we're going to go back to, like I was telling you earlier, the fact that this is set at a low value. Since K is low, okay, what that means is that our reaction progresses to the right. But because K is a very small number, I would expect to have very little amounts of products and mostly reactants, because K is products over reactants. Since K is really small, I would have a very small amount of products and a lot of reactants. Therefore, physically what that means is it goes to the right, but at just a small margin. So I can write in here 1.0 ATM minus X. This is going to be X, and this will be X. I'm just going to kind of 0 plus X is X, 0 plus X is X, 1 minus X is 1 ATM minus X. Well, go ahead and plug all this in. Okay. Now, if I knew what X was, right? If I knew what the value of X was in this problem, I could easily solve this problem, right? Because I just easily plug everything into the equation and solve for X. So that's really the goal of this, is to figure out what X is. Now, to do this, what I'm going to do is I'm going to use the fact that the reaction shifts so far to such a small amount to the right and stays almost all the way in our reactants. That's going to make this easy, because this value of X will be very, very small in comparison to the 1 ATM. Therefore, this value of X here is going to be insignificant. I can actually drop it out. I know it doesn't sound right when you first hear this, but if you stop and think about it, we use our significant figures. If this is a really, really, really small number and I subtract it out, aren't I just going to get back the 1 when I round everything off? And I'll show you what I'm talking about when I'm finished. Okay, this only works if the change between X and my value that I have here is within 5%. So if that difference is higher than 5%, it doesn't work, and you're going to have to use the quadratic formula and plug in and solve for this. So 6.8 times 10 to the minus 9. Okay, you just plug in, solve for the quadratic. You're not going to do that. On the AP test, it is always within 5%. And think about our labs too. In our labs, we can have 5% error. There's nothing you can do about that. There's always a bit error in our labs, and 5% is acceptable. Okay. So with that being said, we can drop out this little bit here and just continue solving. So we have x squared over 1, and then set that equal to 6.8 times 10 to the minus 9. And at this point, it's just a matter of simplifying and solving for x, which comes out to 8.3 times 10 to the minus fifth. Now this is ATM because I'm solving for x, and that's what x is, and these are what the two values of x are. Now notice that this is your answer for carbon monoxide and your answer for chlorine. If I took 1 ATM and I subtract out 8.3 times 10 to the minus 5 from this, and I round using significant figures because it's 0.00083, it's going to round back to 1 using the two significant figure rule when we add and subtract. So therefore, the answer for the phosgen is going to be 1 ATM. Okay, that is a very, very typical problem. This is something you're going to see quite a bit on the AP test. You can see this in a lot in the remainder of the equilibrium section. So make sure you pay attention to this one if you need to watch it again or ask some questions in class. I'll see you guys later. Thanks.